Time doesn't work the way you think it does. I know that sounds like the setup to some pop science nonsense, but I mean it literally. The thing you experience as flowing from past to future, the thing that feels like the most obvious fact about reality, it's wrong. Or at least it's incomplete in a way that should disturb you. Let me tell you about the moment I realized this. Spring of 1940. I get a phone call from John Wheeler, my thesis advisor at Princeton. Wheeler has this idea, this completely insane idea about electrons and positrons. He says, what if they're the same particle? What if there's just one electron in the entire universe, weaving back and forth through time, and every electron we see is just that same particle at different moments in its journey, and every positron is that same particle traveling backward? I thought he was joking. He wasn't. We started working through the mathematics of what that would mean. And what we found wasn't just strange, it was wrong in exactly the right way. Wrong meaning it violated every intuition about how time should work, but right meaning the equations balanced, the predictions matched reality, and suddenly we could explain things that had been mysteries for decades. See, there's this problem in electrodynamics that nobody talks about because it's embarrassing. When a charged particle accelerates, it radiates energy. We've known this since Maxwell, but here's the question that kept me up at night. How does the particle know to slow down? The radiation carries energy away, so the particle must lose that exact amount of energy at the exact moment it starts radiating. But how? The radiation is already gone, traveling away at light speed. What's pushing back on the particle? The standard answer is that the particle creates its own electromagnetic field, and that field pushes back on the particle itself. Self-interaction. The particle talks to itself through its own field. That answer always felt like cheating to me. It's not wrong exactly, but it's deeply unsatisfying. You're saying the particle creates a disturbance, that disturbance propagates outward, and somehow magically, at the exact instant the particle starts moving, it already feels the resistance from radiation that hasn't been absorbed yet. Wheeler and I found a different answer, a better answer. An answer that made Einstein sit up and pay attention when I presented it at Princeton with him in the audience, along with Pauli and von Neumann. Pauli told me afterward that quantizing this theory would be hell. He was right about that. Here's what we realized. Maxwell's equations have two solutions. Everyone knows about the retarded solution, where electromagnetic waves travel forward in time from source to absorber. That's the normal one. Light leaves a bulb, travels through space, hits your eye. Past to future, cause to effect. But there's another solution that's equally valid mathematically, the advanced solution. Waves that travel backward in time from absorber to source, future to past, effect to cause. Most physicists just throw that solution away. They say it's unphysical, it violates causality, it can't happen. But mathematically, it's right there in the equations, just as valid as the forward-traveling waves. Wheeler and I said, what if we keep both? What if electromagnetic radiation actually consists of both retarded waves going forward in time and advanced waves coming backward in time, and they meet in the middle? When you work through the math, something beautiful happens. The two waves combine to produce exactly the resistance that the accelerating charge experiences. The future absorbers send waves backward in time. Those waves converge on the charge at the exact moment it starts accelerating, and those backward traveling waves create the drag force that extracts the radiated energy. The particle knows to slow down because the future is already telling it to slow down. Read that again. The future affects the past, not through some mystical force, not through consciousness or quantum woo, but through perfectly ordinary electromagnetic waves that happen to be traveling the wrong direction through time. And here's what really bothered me about this, what kept me thinking about time for the next 40 years. If you look at the final result, at what an observer actually measures, you can't tell the difference. You can't distinguish between a world where only retarded waves exist and a world where both retarded and advanced waves exist, but cancel in just the right way. The time asymmetry we see, this arrow of time pointing from past to future, it's not fundamental. It's a consequence of how we label things. If you swap the labels emitter and absorber, the time direction reverses, but the physics stays exactly the same. The universe is time symmetric at its core. The arrow of time is something we impose on it, not something that's actually there in the fundamental laws. That realization changed everything, because if time symmetry is fundamental, then particles moving backward in time aren't just mathematical curiosities, they're real. In the spring of 1940, Wheeler called me on the telephone. I was a graduate student. He was already a professor, and he had this crazy idea bouncing around in his head. He said, what if there's only one electron in the entire universe? One electron, not trillions upon trillions spread across every atom, just one, moving forward through time, then backward, then forward again, weaving through space-time like thread through fabric. Every electron we see is the same electron at different moments in its incredibly long, tangled journey. And when that electron moves backward through time, we see it as a positron, an antiparticle. I told him the idea had problems. If there's only one electron, why do we see so many? Why aren't there equal numbers of electrons and positrons? But the core insight stuck with me. It wasn't that the one electron universe was right. It was that thinking about particles moving backward through time wasn't crazy. It was legitimate physics. This became central to everything I did afterward. In quantum electrodynamics, in my diagrams, I started drawing antiparticles as particles traveling the opposite direction through time. A positron going forward looks identical to an electron going backward, not as a metaphor, as actual physics. Draw a diagram of an electron and positron annihilating into two photons. The electron comes in from the left, moving forward through time. The positron comes in from the right. They meet, they annihilate, two photons shoot out. Standard picture. Now redraw it. The electron comes in from the left, moving forward. At the collision point, it doesn't annihilate. It reverses direction in time. It's now moving backward, which means we perceive it as a positron moving forward. The two photons are emitted at the moment of reversal. Same physics, different interpretation. Both are valid. This wasn't just mathematical games. When you calculate probabilities in quantum mechanics using this picture, you get the right answers. The universe genuinely doesn't care which description you use. Time direction at the particle level is ambiguous. Let me make this concrete. You're watching fundamental particles interact. An electron scatters off a photon. Standard story. Electron absorbs photon, changes direction, moves on. But here's another story that's equally true. The electron moves forward in time, emits a photon, and recoils backward through time briefly before reversing again. From your perspective, watching from outside, you can't tell which story is correct. Both give identical predictions for what you'll measure. The mathematics forces this on you. When you write down the equations for quantum electrodynamics properly, particles propagating backward through time aren't optional extras you can ignore. They're required. They're part of the calculation. Virtual particles in Feynman diagrams, these temporary fluctuations that pop in and out of existence, some of them are going backward. They have to be, or the math doesn't work. Now you might think this is abstract, irrelevant to everyday life. Wrong. Every time you see light, time-reversed electrons are involved. When a photon hits your retina, an electron in a molecule absorbs it and jumps to a higher energy state. The calculation for that process includes contributions from paths where the electron briefly moves backward through time. These contributions are small, but they're measurable. Quantum electrodynamics has been tested to 10 decimal places. The agreement with experiment is absurd, and that agreement includes all the backward time-traveling paths. This is where things get philosophically dangerous. If particles can move backward through time at the microscopic level, why can't we? Why is there an arrow of time at all? I spent years thinking about this. The fundamental laws of physics are time-symmetric. If you film atoms interacting and play the film backward, you can't tell. The reversed process obeys the same laws. Electrons repel each other going forward, they repel each other going backward. Conservation of energy works both directions. Momentum, angular momentum, all the conservation laws are time-symmetric, yet you can tell if a film of everyday life is running backward. Eggs don't spontaneously reassemble. Broken glass doesn't leap off the floor and reform. Heat doesn't flow from cold objects to hot ones. There's an obvious arrow pointing from past to future. Where does that arrow come from if it's not in the fundamental laws? I finally understood it isn't about laws. It's about initial conditions. The universe started in an extraordinarily special state, low entropy, incredibly organized. And entropy has been increasing ever since, not because the laws demand it, but because there are vastly more high entropy states than low entropy ones. The arrow of time is statistical, but that means something profound. The time asymmetry we experience, this feeling that past is fixed and future is open, that causes precede effects that we remember yesterday but not tomorrow, none of that is fundamental. It's emergent. It comes from the special state the universe happened to start in. At the level of individual particles, time is reversible, and if you could somehow prepare a system in exactly the right final state, it would evolve backward toward its initial state, just as naturally as it evolved forward. The laws permit it. Here's what really gets me. Wheeler and I worked out this absorber theory, and it demands something extraordinary. When I turn on a light bulb, I'm not just sending radiation forward into the future. According to our equations, the light interacts with every charged particle in the future universe that will eventually absorb it. Those future absorbers send waves backward through time to the moment I flip the switch. The energy extraction happens because of a collaboration between future and past. The resistance I feel when accelerating a charge exists because the future is pushing back. Think about what that means. The radiation from your desk lamp depends on the existence of future absorbers, potentially billions of years from now. If the universe were different in the future, if there were no matter out there to absorb the light, the bulb wouldn't radiate the same way today. The future shapes the past just as much as the past shapes the future. We presented this to Einstein, Pauli, von Neumann. Pauli immediately saw how difficult it would be to make it work with quantum mechanics. Einstein wondered if you could apply the same thinking to gravity, but what struck me most was how uncomfortable everyone felt with the idea that future events could influence past ones. It violated something deep in how we think about causality, yet the mathematics insisted. And when I developed the path integral formulation, this time symmetry became unavoidable. A particle getting from point A to point B doesn't take one path. It explores every possible path simultaneously. Some of those paths loop backward through time before moving forward again. You can't exclude them. They contribute to the final amplitude. I spent years working with these equations before I really accepted what they were telling me. Your intuition screams that the past is fixed and the future is open, that causes must precede effects. That information flows one way through time. But at the quantum level, none of that holds. An electron doesn't know which direction is future and which is past. The equations treat both directions identically. So where does the asymmetry come from? Why do we remember yesterday but not tomorrow? Why does heat flow from hot to cold but never the reverse? Why do eggs break but not spontaneously reassemble? I struggled with this until I realized the answer isn't in the laws. It's in the boundary conditions. The universe started in an incredibly special state, extraordinarily low entropy, everything packed together, organized, uniform, and ever since, entropy has been increasing, not because the laws force it to, but because there are overwhelmingly more disordered states than ordered ones. If you film individual atoms colliding, you can't tell if the film is running forward or backward. The collisions look the same either way. But if you film a whole room full of gas expanding, you can immediately tell which direction is forward. The gas spreads out. It never spontaneously compresses into one corner. That's not because compression violates any physical law. It's because there are vastly more ways for the gas to be spread out than compressed. The arrow of time is statistical. It emerges from probability, not from fundamental physics. And that means at the microscopic level, time really is reversible. If you could prepare a system in exactly the right final state, it would evolve backward just as naturally as it evolved forward. This has profound implications. The distinction between past and future, this thing we take as absolutely fundamental to how reality works, isn't fundamental at all. It's a consequence of the particular history our universe happens to have. In a universe that started in a high entropy state, there might be no arrow of time. Past and future would be interchangeable. Now, does this mean time travel is possible? Can we actually go backward? The equations allow it under certain circumstances. Wheeler and I showed that if backward in time influences exist, nature would arrange itself to avoid paradoxes. The universe would find self-consistent solutions. If you tried to go back and prevent your own birth, something would always stop you, not because of any prohibition, but because inconsistent histories don't exist as solutions to the equations. But practical time travel for macroscopic objects, that's different. The second law of thermodynamics still holds statistically. You can't decrease the entropy of the universe as a whole, and any attempt to send information backward through time would require manipulating that initial low entropy state, which we can't access. Yet at the quantum level, it's happening constantly. Virtual particles propagating backward through time are part of every interaction. The future influencing the past is built into how electromagnetic fields work. Time isn't what you think it is. It's not a river flowing in one direction. It's a dimension, symmetric, reversible at the fundamental level. The asymmetry you experience is real, but it's not fundamental. It's statistical, emergent, dependent on initial conditions. And that changes everything about how you understand reality. The past isn't absolutely fixed. The future isn't absolutely open. They're both parts of a single space-time structure where the direction we call forward is only special because of how the universe happened to begin. So what does this all mean for you sitting there right now experiencing time as this undeniable flow from past to future? It means the flow is an illusion, not a comforting illusion, not something that makes life easier to understand, but an illusion nonetheless. The universe at its deepest level doesn't distinguish between forward and backward. That distinction exists only in your memory, in the entropy gradient of your particular corner of space-time, in the accident of initial conditions that set everything in motion 14 billion years ago. Every moment you've lived, every choice you've made, every consequence you've experienced, all of it exists simultaneously in the four-dimensional structure of space-time. The past isn't gone. The future isn't yet to come. They're both there, woven together with the present into a single geometric object. And particles are constantly moving through that structure in both directions, forward and backward, contributing to what you perceive as the present moment. Does that make your experience of time less real? No. It makes it more interesting. You're not watching a movie that's being projected frame by frame. You're part of a vast, interconnected web where cause and effect blur together, where future and past influence each other, where the direction of time emerges from probability rather than being carved into the bedrock of reality. That's what kept me up at night for 40 years. That's what made me question everything I thought I knew about how the universe works. And that's what the mathematics insisted on, again and again, no matter how uncomfortable it made me feel. Time doesn't flow. We flow through it. And the direction we're flowing isn't as fixed as you think.